Introduction. Hi Ram, how are you? I am good. And what about you? Fine. What are you doing on laptop? I'm just doing my physics assignment, alternating current. I will complete this in 10 to 15 minutes. Okay, I want to ask you something. Yes, so you must know that laptop works on DC voltage as it has a battery and laptop gets charged by plugging the charger in the AC voltage. My question is that how is it possible that laptop works on the AC voltage? I really don't know about that. Okay, let me tell you that laptops and many appliances also work on the DC voltage. When the charger is plugged into AC supply, then the charger converts the AC voltage into DC voltage so that the appliances can work smoothly. Okay, I got it. It's interesting. Tell me more about it. Children, today we will study about the alternating current. Objectives. At the end of this lesson, you will be able to define alternating current, define, differentiate between alternating and direct current, calculate AC voltage applied to a resistor, calculate root mean square value of current and voltage, calculate AC voltage applied to an inductor and capacitor, define inductive reactance and capacitive reactance. Definition. As an generator produces an alternating voltage that varies sinusoidally with time, such a voltage is called an AC voltage, and the current driven by it in a circuit is called an AC current. The electrical main supply in our homes and most of the electrical appliances we use today require AC voltage. The main reason for preferring use of AC voltage is that it can be changed conveniently and efficiently to either higher or lower amplitudes by means of a transformer. Alternating current or voltage. The conditions for a periodically varying current or voltage to be termed as alternating are following. Every cycle corresponding to one time period has half positive and half negative value alternately. In case of current, it means that direction of current reverses after every half cycle, and in case of voltages, it means that the polarity of potential difference reverses after every half cycle. The positive and negative half cycles are exactly symmetrical. The amplitude of current or voltage on both positive and negative sides remains constant in all cycles. Difference between alternating and direct current. AC cannot produce chemical effects of current, but DC can produce chemical effect of current such as electroplating or electrolysis. AC can be stepped up or stepped down by transformers, but transformer is of no use for DC. AC can be converted into DC by using electronic rectifiers, whereas DC can be converted into AC by inverters. AC voltage applied to a resistor. We consider a circuit consisting of a resistor of resistance R and an AC EMF source. The AC voltage across the terminals of the source varies sinusoidally with time according as V is equal to Vm sin omega t, where Vm is the amplitude of alternating voltage and omega is the angular frequency. We apply Kirchhoff's rule in the loop to get I is equal to Vm upon R multiplied by sine omega t. The maximum current given by Vm upon R. Now the above equation can be written as I is equal to Im sin omega t. At any instant, the voltage across the resistor is given by Vr is equal to IR. By putting the value of I, we get Vr is equal to Vm sin omega t. Above equation show that in an AC circuit, the current through a resistor is in phase with the voltage across its terminals. Root mean square value of current and voltage. Let us consider the sinusoidal voltage and current given by V is equal to Vm sin omega t. I is equal to Im sin omega t. Both V and I are positive for one half of the cycle and negative in the other half. Therefore, the average value of a complete cycle is 0. Root mean square current. The square root of the average value of the square root of current is called the root mean square RMS current. IRMS is equal to Im upon root 2, which is equal to 0.707 Im. In the same way, the RMS voltage is related to the maximum value of the alternating voltage, as Vrms is equal to Vm upon root 2, which is equal to 0.707 Vm. The resistance R in a purely resistive circuit has the same value at all frequency. A graph of resistance versus angular frequency is a horizontal straight line. Example of instantaneous voltage. Let's take an example of instantaneous voltage. The electrical mains in a house are marked 220 volt 50 Hz. Write down the equation for instantaneous voltage. Let's see the solution. Given values are EV is equal to 220 volt, nu is equal to 50 Hz. We know that EV is equal to E naught divided by root 2, or E naught is equal to root 2 EV. On putting the values in the equation, we get E naught is equal to 311 volt. Also, we know that omega is equal to 2 pi nu. On putting the values in the equation, we get omega is equal to 314 radian per second. Hence the instantaneous voltage is given by is equal to 311 sin 314t. Power delivered to a resistor. The instantaneous power supplied to the resistor is given by PR is equal to VI, which is equal to the product of Vm sin omega t and Im sin omega t. It can be written as PR is equal to product of Vm, Im and sin square omega t. The average power supplied in one complete cycle is given by PR is equal to Vm multiplied by Im divided by 2. Since the time average of sin square omega t over a complete cycle is 1 by 2, It can be written as PR is equal to VRMS into IRMS, or PR is equal to IRMS square into R. Representation of AC current and voltage by rotating vectors. The phase relationship between the current and voltage in an AC circuit can be easily determined by using a technique which involves phasors. The diagrams containing phasors are called phasor diagrams. In this technique, voltage and current that varies sinusoidally with time are represented by rotating vectors V and I called phasors, whose lengths represent the maximum voltage Vm and maximum current Im. Consider the phasor diagram for an AC resistor circuit. The phasors V and I are collinear as they rotate because the voltage and the current are in phase. At time t, the phasors make an angle omega t with the positive x-axis. AC voltage applied to an inductor. Consider an AC circuit consisting only of an inductor of inductance L connected to an AC source. The AC voltage across the source is equal to Vm sin omega t. The changing current output of the AC source produces a black EMF in the coil of magnitude given by BL is equal to LdI by dt. We apply Kirchhoff's rule in the loop to get V minus VL is equal to 0. Now put the values in the above equation. Di by dt is equal to Vm upon 1 multiplied by sin omega t. Now integrating both sides with respect to time, we get I is equal to Im sin omega t minus pi by 2. The amplitude of the oscillating current is written as Im is equal to Vm upon omega L. Inductive reactance. From the expression Vm upon omega L, we see that the quantity omega L plays the same role of resistance and is called the inductive reactance of the inductor, denoted by XL. XL is equal to omega L. The amplitude of the current in a purely inductive circuit is given by Im is equal to Vm upon XL. Power delivered to an inductor. The instantaneous power supplied to the inductor is given by negative Vm. Negative Vm Im by 2 multiplied by sin 2 omega t. Since the time average of sin 2 omega t over a complete cycle is 0, therefore inductor power is equal to 0. Phasor diagram of an inductive circuit. Phasor diagram. In an AC circuit, the current through an inductor lags the voltage across its terminals by pi by 2. At the points on the current graph where the current is 0, the graph is at its steepest and the current has the largest rate of increase or decrease. Thus, voltage and current are not in phase but are 1/4 of a wave cycle out of phase. AC voltage applied to a capacitor. Consider an AC circuit consisting of a capacitor of capacitance C and an AC source. The AC voltage across the source is V is equal to Vm sin omega t. If Q be the charge on the capacitor at any time t, then the instantaneous voltage across the capacitor is given by Vc is equal to Q divided by C. We apply Kirchhoff's rule in the loop to get V minus Vc is equal to 0. Now we put the value in the above equation. Vc is equal to Vm sin omega t. The instantaneous current in the circuit is given by Im sin omega t plus pi by 2, where Im is equal to omega c. Vm is the amplitude of the oscillating current. Capacitive reactance. The above expression Im is equal to omega c. Vm can also be written as In is equal to Vm divided by 1 upon omega c. The capacitive reactance Xc of the capacitor is given by 1 upon omega c. The amplitude of the current in a purely capacitive circuit is given by Im is equal to Vm upon Xc, or Irms is equal to Vrms upon Xc. Power delivered to a capacitor. The instantaneous power supplied to a capacitor is given by Vm Im upon 2 multiplied by sin 2 omega t. Since the time average of sin 2 omega t over a complete cycle is 0, therefore capacitor power is equal to 0. Phasor diagram of a capacitive circuit. Phasor diagram. In an AC circuit, the current through a capacitor leads the voltage across its terminals by pi by 2. When voltage increases from A to B, the charge on the capacitor increases and reaches its full value at B. However, the current representing the rate of flow of charge has a maximum positive value at the start of the charging process at a dash. While the capacitor voltage decreases from B to C, the charges flow out of the capacitor in a direction opposite to that of the charging current, as indicated by negative current from B dash to C dash. Thus, voltage and current are 1/4 wave cycle out of a step. Did you know the first alternator to produce alternating current was a dynamo electric generator based on Michael Faraday's principles constructed by the French instrument maker Hippolyte Pixii in 1832. Inductor cannot reduce direct current, it can reduce only alternating current. Capacitor allows alternating current to flow through it but blocks direct current. Summary. Let us summarize what we have learned so far. An AC generator produces an alternating voltage that varies sinusoidally with time. In an alternating current, every cycle corresponding to one time period has half positive and half negative value alternately. In an AC circuit, the current through a resistor is in phase with the voltage across its terminals. The square root of the average value of the square of the current is called the root mean square current. In phasor diagram, voltage and current that varies sinusoidally with time are represented by rotating vectors V and I called phasors, whose lengths represent the maximum voltage and maximum current. In an AC circuit, the current through an inductor lags the voltage across its terminals by pi by 2. In an AC circuit, the current through a capacitor leads the voltage across its terminals by pi by 2.